Okay, let's tackle another question. We have a string of some length L having tension T carries a transverse wave at speed V. The radius of the string is halved and the tension is increased 4 times. Find the new speed of the wave in the string. Okay, in order to solve this problem, we need to understand more about speed. Now we already know one equation for speed, so let's talk about speed of a wave. Okay, speed of waves. Okay, at first you might say, well, we already know an equation for speed of the wave. V equals f lambda. Isn't that an equation for velocity of a wave? Well, not really, because remember, velocity does not depend on frequency, nor does it depend on wavelength. Remember, the real formula is lambda is v divided by f. Please remember that. Okay, so yes, if I give you the frequency and wavelength, of course you can calculate what the speed is using this formula, but the speed is not decided by these two people. What decides the speed of the wave? Speed of the wave purely depends upon the medium. Okay, I think I've explained that before. It depends on the medium, the properties of the medium. All right, and the frequency depends on the source. The wavelength gets decided by the speed and the frequency. Okay, so how does it depend on the properties of the medium? Well, I will write one general formula which we'll use for different cases. The general formula for speed, I would like to write it as it'll work for most of the cases that we'll be talking about. That will be a square root of, I'm gonna write this as E divided by I. So what is this E? E is the elastic property. So elastic property. I mean, think about it. Elastic property is the property of an object to get deformed and then it returns back to its original shape. If objects don't have any elastic property, there's not going to be any wave over there. So forget about the speed. Think about any material. For example, water, it's elastic because it can deform. What about strings? Even they're elastic. Okay, so clearly depends upon elastic property. And there's one more factor that decides what the velocity is. Notice, more the elastic property, more elastic it is, higher will be the velocity of the sound, velocity of the wave, it can be any wave. And the second property, which is going to impede the velocity, see, it's inversely related to that, and that's going to be the inertial property. Okay, so inertial property. It has something to do with mass, but not directly mass. Most of the times it will be some sort of a density. So how dense the material is. More density, more number of particles per meter or per meter square or whatever, you will see it becomes harder, or the energy travels slower. So the speed will decrease with higher values of density. All right. So with that in mind, let's talk about the speed of waves in different cases. So the first thing I want to talk about is speed of transverse wave in a string. Transverse wave in a string. And the reason I say transverse, because you can generate longitudinal waves in strings as well, and that will be completely different than what I'm talking about. So what's going to be the formula for the speed of a transverse wave in a string? Okay, we need to ask ourselves, which elastic property of the string allows the transverse wave to occur? Well, let's see. A wave in a string would look like this. So you see the string is getting deformed. It's going up and it's going back down. It's getting deformed this way. What elastic property allows that deformation and that decides how much it gets deformed and how quickly it comes back? And the answer is tension. I mean, think about it. If the string is very highly tensed, then you pluck it and immediately it comes back down. If the string is slacking, you pluck it, it takes time to regain its own shape. So higher the value of tension, faster will be our wave. So tension is the elastic property that comes in the numerator, divided by inertial property, density. Now, when we are talking about a string, we're going to treat it as a one-dimensional medium, right? I mean, we can neglect all the area and everything, cross-sectional stuff. All right, anyways, so Since it's one-dimensional, we're going to use linear density. So mu. Okay, so mu, this guy, is linear density. So that's mass per length. And notice these two are constants. For a given string, there will be a particular value of tension and there will be a particular value of linear density. So it doesn't depend on the source. Okay, that's for transverse wave in a string. Okay, now let's talk about speed of sound. A sound can travel in solids, they can travel in liquids, they can travel in gases. So let's talk about formulae. Well, the speed of sound in solids will be, so let's talk about solids first. We're going to use the same property. It's going to be square root of the elastic property. And the question now is, what is the elastic property that allows the waves to propagate in sound? Well, again, like I told you that time, you can have a wave traveling in, for example, a solid like this. You can have a wave traveling through this. You can have a sound wave. You can think of this as a spring, okay? And particles will start vibrating this way and the wave propagates this way. Okay, so what elastic material are we going to talk about? Well, we're going to talk about deformations that happen along the length, right? The deformations, and that is taken care by what we call as Young's modulus. Okay, so Young's modulus comes over here and we divide by the density. So the volume density is what we're talking about over here. Okay, so volume density. Okay, if you have not seen this before, there are proofs available, but we're not going to talk about the proofs. All right, so one last thing we're going to talk about is speed of sound in fluids. Okay, since fluid is bulk matter, we're going to use instead of the Young's modulus, we're going to use the bulk modulus and divide by density. Okay, and especially for gases, so this can be used for liquids. Okay, it can be used for gases also, but for gases we can refine this. Okay, so for gases, we can prove that the bulk modulus has to be equal to gamma times P, where P is the pressure and gamma is gamma. Okay, divided by rho. What is gamma, you ask me? Well, gamma is the ratio of Cp and Cv. You should know this stuff by now. Okay, so it's the atomicity, and P is pressure. That's pressure, good old pressure. It can be proved that the bulk modulus is equal to gamma times P, and this was actually proved by Laplace. You must have heard of Laplace correction of Newton's formula, and this is true when the speed of the sound is traveling in an adiabatic condition. Adiabatic condition, which is the case in almost all the gases. Okay, Newton thought it was isothermal case. In an isothermal case, you will see the bulk modulus turns out to be just the pressure, but in the adiabatic case, the bulk modulus becomes a little bit more, and there is the gamma coming into picture. Okay, so these are the things you need to understand for speed of a wave. Now that we understand the speed of a wave in a medium, we can now tackle our question. Alright, so what's given to us is we have